we're in triage mode here. We can we need to cover some significant material quite quickly, but I felt to be negligent to put the details of the rewriting rules like in perspective by talking about how they fit into this overall framework of algebraic ABMs that's falling into place. This is a system that's moving forward. As I understand it, Chris Brown is working as we speak on some major components of this, or this week. And it's looking hopeful that come May, there'll be another hackathon in Edinburgh to advance this for 6 weeks. And I want to talk where we're going. I know on a day-to-day basis, progress seems slow. But there's a lot going on, actually. And I want to talk about the overall design, because I think you folks, by virtue of going through this course, you'll be uniquely equipped to understand a lot of things in this right now. And I think you might appreciate, just seeing how these things slot together. Okay, so one thing is this framework adheres to this philosophy of separating out what the state is, what's changing over time, the governing processes that update that state, and then the particular runtime situation in a given run of one of these. These are more like the processes that shape the evolution of the state. This is what happens to play out in a particular run, which often will have stochastics. Okay, so this framework that we're talking about here, what does it involve? Well, it involves two big things in their interplay, okay? Or arguably three big things. There's rewrite rules and continuous dynamics having to do with this, but there's a broader context here, like involving networks or involving people's location, which is overarching this. And I want to put this data migration into context so you understand where we're going, and I want to put it, talk about the design of this overall framework. So the idea here is that we want to be able to compose a model out of pieces. Like there might be pieces associated with smoking and pieces associated with heart disease and pieces associated with networks. But these are not solitudes, right? There's some overlap, just like with push-outs. Remember, we could fuse things around a common point. Remember that with composing stock flow models. We compose them around a certain point. And that's the idea here, okay? And as you go out from a more narrow model to a broader model, you use data migration to move, okay? And an important part is that as one of these pieces evolve, you should be able to sort of evolve that piece and just compose it with the rest of the model, which hasn't had to evolve, to get a new updated model, okay? So you can update the pieces without it affecting everything. And something that we didn't have time to talk about, which is kind of nifty, and where there's built-in support to be offered for it, that will be rolled out real soon now is the plan, probably in the next year, is we have this model composed out of pieces, and maybe there's some state charts, some network information, maybe some system dynamics, stock flow models. But what's really interesting is you have schemas for the different pieces, okay? So this has schema associated with it. This has a schema. This has part of it, or a fraction of a schema. It's actually not a full schema. It's like a schema fragment, okay? And then you can take push-outs of those schemas. Do you remember the notion of push-out? So I might say, for example, P here is the same as P down here, or something like this. Or this might be a vertex, and I'll say vertex here is the same as P down here. And it will kind of glue those together. Do you remember that notion? Remember the Tinker Toy idea? You stick them together. It's just like that. And so something that is supported is push-outs of schemas, or these schema fragments. And Xiaoyan has implemented a schema of schemas, which is kind of nifty. And you can kind of glue together these sub-schemas into an overall schema for the model. And you can glue them together modularly. You know, a sub-schema for each of these things, you glue them together, you say how they overlap, how heart disease affects smoking, or how smoking is affected by networks. But you can glue them together or stick them together like a Tinkertoy. Okay, that's the idea. And Xiaoyan has implemented this and uses it in her code. GATLab, GATLab actually does this at a higher level, even for things encoded in different, what's called theories, which differs in a broader way. It has some particular issues with doing it with things, what are called schemas, which are older, and it doesn't yet fall support. But we're told that the support for it is going to roll out for doing push-outs of schemas. And if we pushed for it, we'll probably be rewarded by getting it sooner. Okay, so the idea, broadly, what we're hoping to do is build up an ABM out of pieces. Nicotine use piece, heart disease piece, diabetes, geographic space, whatever. And each of these is not a solitude. They can be glued together around certain points, right? With kind of push out type ideas or structured co-spandy kind of interfaces that get identified. Remember that? So that's kind of roughly the set. And don't take this too seriously, but the idea is that we should be able to build up our model out of these composable pieces, which we compose together using the sort of tools we've been talking about, like structured co-spands. Now, a key part of this is what you've been applying throughout the semester, which is CSATs. But please do realize that CSATs in this design can encode like discrete things, like maybe someone's age group, edges between people. But, well, I guess that would be relational attributes. Also continuous attributes, like someone's weight or someone's blood sugar level, as described by a stock flow diagram, for example, or ordinary differential equations. Now, CSATs, this may not be obvious, but one thing you haven't heard me talk about is how our framework is going to use messages. Because one thing we realized early on the hackathon, it was a big revelation for me. I was thinking messages are needed, we're going to need to get them in there. And it turns out most of the things for messages, ways we can get messages can be achieved by content pattern matching. You have to kind of think about it for a bit, but most of the way the message is used are to like coordinate between agents. And at least for the examples I've thought of, it seems that pattern matching, when this situation applies, do this, will allow us to capture those things more elegantly than a message. A message it's very powerful, but it's like a power tool. And with a power tool, you can accidentally cut off fingers and so on. You can have bugs really easily introduced. It's kind of like go-to statements in programming. You can have spaghetti code where like the message is just this very unconstrained, under-constrained, under-disciplined way of doing things. Turns out pattern matching, saying when this applies, do this, can coordinate more effectively. And I will say that a lot of the things I find that I would do in any logic as nesting of agents. Let's say each person has a list of drugs within them, and they have for each of those drugs some state chart indicating the resistance status or something. It turns out that you can do it much more elegantly, much to the heart of the matter through relations, by saying there's a relation between people and drugs. We don't need nesting. As useful as it might be sometimes to have nesting, have hierarchy, here we don't need it, actually. Here we need a relation. And a lot of what I'm discovering is like these idioms we use in AnyLogic and other platforms like Repast or NetLogo, like a lot of them are somewhat forced by the limitations or the limited affordances of those frameworks. And where I thought nesting used to be required or messages been required, I realize now, wait a minute, there's much more elegant ways to do it relationally, using the powers of these relational components. Now, one thing you've seen in this course is this AC set colim, right? It allows this very declarative way of saying, you know, there's a sheep and a wolf, and the wolf location is the same as the sheep location. Let it be, and then we will match that pattern, find all cases where sheep and wolves are at the same location, right? That's the idea, and that's how we want to be able to sort of describe conditions, not as some arbitrary Java code, not as some arbitrary Python code, but using sort of declared things, find this pattern. That's a lot of the design here. Okay, I want to talk about dynamics though, because there's an important story here. Dynamics here from the get-go involve two things: rewriting rules and ordinary differential equations, or you could think of it close to my heart is using it for stock flow. At the end of the day, the idea is for example, ODEs, you could produce them via stock flow. That's the one down here. From electrical circuits, from Petri nets, like they might actually come from many sources. Sometimes you might actually want to specify them manually, but a lot of the times they might come from different things, and maybe you want to weave them together. You want to compose them like sets of ODEs. But for me, the main one that I care about the most is stock flow. But it won't be the only way you can interpret a stock flow diagram. You might interpret it, as Nestor knows, as stochastic rewriting. Okay, so let's talk about these two types. So there's rewriting alongside ODEs. And there's a story here that's quite rich, because these two are not solitudes. This one can influence this and vice versa in multiple ways. You're familiar with rewriting. I don't have to talk with you about this. But I want to hit that first. We'll talk about this, and then we'll talk how they work together. So you've seen rewriting. One thing we didn't get a chance to talk about, but which is an important part of this, is there are these things called application conditions, which basically mean, most importantly, that you can say this rewrite rule applies for the most part, but don't apply it in this case. Even though it might match, don't do it in this case. And you may wonder, like, why do that? Because in general, it's hard to say where the rewrite rule separately by itself when not to fire. Sometimes you can say, like, oh, if it's two susceptibles, you know, like one person is infective, one is susceptible, apply this. Well, then you might think, well, if that's the only rule, it's not going to do it with two susceptibles, and that's true. But there are cases where, like, you might want to say, well, look, apply this if there's a mother with one fetus, but don't apply that rule if it's with twins or something like that. We'll put in another rule for twins. And it turns out there's a way to encode negative application conditions. And I don't fully grok this, but I think it has, there's a notion that saying negatives, you can't test the negatives here like in code. So we need a way of declaratively saying, are there conditions under which you do not want to apply this rule? That's often a very useful thing. So here's one, like, okay, we have a person who has a fetus with a certain weight and a certain age, gestational age, and the mother has a certain gestational age. And we want to perhaps apply this on the left-hand side of her rewrite rule, except if that mother has two fetuses, two feet. Now, you might, again, say, well, wait a minute, can't you encode that in the rule? Well, if you think about it, without this now a negative application condition, this rule would apply in this case, right? It would apply for the first one, right? It would say, hey, here's a match. It would apply for the second one. It would say, here's a match. But this is saying basically don't apply it if you have two fetuses. I'll handle that separately, basically. And it can prevent this kind of matching it in contexts where it would otherwise match. It can say, don't, contraindicate, don't match it when we have this sort of broader context, which is hard to do in a rewrite, like on the left-hand side. What would you do? You could specify when to apply, but not when not to, without this. So this negative application condition called a knack is actually pretty important. And you can develop, Chris Brown has a knack for spotting when these are needed, if I can take the pun painfully. Yes.
I just want to bring light to Eric's question.
Oh, I didn't see it. Yeah.
Sorry, I want to.
Okay, great. That's on. How do we handle modularity? Is there research on the same concepts, but in the concepts of classes, modules include? Oh, this sounds a lot like how we handle modularity. Yeah, it is quite aligned, I think, Eric. In object-oriented software engineering, but more generally in rigorous software engineering, there's, a key desire to separate interface from implementation, right? You separate out the kind of the ports, the things that can be plugged together from the heart of the implementation, from the vagaries of how it's implemented. You separate out what it does from how it realizes it so it can evolve. And in many ways, that, Eric, has fed into this design here. It's kind of this ability to plug things together modularly and allow each of them to evolve separately where needed. Yeah, it is by design somewhat similar, but there's convergent evolution, right? Like the same knowledge of how scalable systems have to plug together. It motivates choices in procedural software engineering of certain ways and object-oriented software engineering, adaptation of those techniques here as well. Okay, so these themes reappear in many places, and indeed many areas of life, right? You have a standardized plug size because you want to separate my ability to plug something into the wall from the vagaries of how the wiring is behind the point. I want to be able to plug into the wall regardless of the details of exactly how it's wired up back there. What color the wire is. Imagine if I had different plugs based on, is it a orange wire or a red wire or or green wire? It would be chaos, right? We need standardized interfaces to plug things together. That's kind of it. Now, one thing I want to expand here, though, on is, so we have these negative application conditions. We didn't have time to talk about them, but they're actually quite important in this agent-based modeling context to contraindicate certain expansions. I want to talk, though, about something else we didn't talk about. When rewrite rules are matched, sometimes we want to immediately update. Sometimes we want it, when it matches with a certain rate, do this. So maybe we match someone's in the in the infective state, and with a certain rate of 10% per day, they'll recover. They'll go to the recovered state. So there it's like a hazard rate, certain chance per unit of time that they'll recover. And we want that to apply when this rule matches. They're in the in the effective state, it's like we set this hazard rate on so that over time they have the chance of leaving unless their state updates, right? Or again. Okay, now stock and flow, what do we plan to use? Well, we plan to use stock and flow. Okay. One thing I'm not telling you yet, but I'm gonna let you in on the secret. The main way we anticipate doing rewrite rules in this package is that they won't be hand-coded. Some rewrite rules can be hand-coded. That's great. You have generality and it's declarative. Rewrite rules are quite nice. They can be declarative. But actually, most of them, we don't anticipate being hand-coded. They're going to come from, and the main one I have in mind, it's not the only one, is statecharts.jl. A state chart will compile down to rewrite rules behind the scenes. Rewrite rules like if the agent's in the effective state, a hazard rate goes and they will transition to recovered state at a certain time. It will turn into those rewrite rules. Now, those rewrite rules will be declarative and they'll support reasoning about it, but the user won't generally see them unless they want to. But they can be translated into these broader and broader contexts. It's this idea of sort of translating the rule to where networks apply or where physical location applies or whatever. So this is this is part of the plan. There may be other sources of rewrite rules. Let me give you another one. Algebraic Petri. Petri nets are another way, particularly if you have like two things that come together to form a third. This doesn't happen as much in most agent-based models that I use, but you could imagine it particularly in some chemical systems, right? Like two atoms of hydrogen and one atom of oxygen come together to form H2O, right? This is where Petri nets are used. And there's probably, if you think about assembly of maybe
individuals to a community.
Yeah, exactly. Or individuals to a community organization that they join, or doses of vaccine in a person yield a vaccinated person. The vaccine is used up, right? Normally, like with a rewrite rule, I don't think of like susceptible effective and the effective is used up. That doesn't happen, right? It's not of that sort. But Petri nets do characterize these consuming processes, and they can produce rewrite rules too. So these rewrite rules we've been talking about, although I like them a lot, I don't want to have to burden most modelers with the details of writing them. Most of them, 80%, 90%, maybe above that, will be automatically produced and automatically migrated because of it, okay? Now, I want to talk, though, about stock flow model for a second. Stock flow models, likewise, will be produced by multiple frameworks. They'll be produced by stock flow. ODE models. We produced by stock flow. They could be produced by Petri nets. Turns out Petri nets have a so-called mass action interpretation whereby they could turn into ODEs. ODEs can also be produced by, some sort of system for solving like electrical networks, circuits or whatever we saw earlier. So maybe sometimes you want to specify these in a different mechanism, but I see mostly them being specified by stock flow for most of our models. And it's the same old stock flow that you've learned about in this course. It's the same old. So how do these interact? Well, I don't want to dwell on this too much because we have too much to cover. But let's just say rewrite rules can affect state variables, can affect stocks, right? I mean, this is true in any logic, right? You could have like an event go off and it changes the value of the stock, right? But more powerfully, it can change like the collection of flows into and out of the stock. So maybe the mother's blood sugar here, and I don't know if I have a nice picture on it, but maybe when a person becomes pregnant, the mother's blood sugar now depends also on the fetus's metabolism. And so during the time of the pregnancy, her blood sugar has this extra flow into and out of it. And then when she delivers, when she reaches term and the baby's delivered, that flow will disappear from her blood sugar and it'll be back. So the idea is that like rewriting could affect the form of the stock flow model, if you see what I mean. And then ODEs can impact CSET rewriting, like whether or not a pattern matches. You know, is someone's level of fentanyl in their system above a certain level, or their viral load above a certain level, or their blood sugar above a certain level. It could also affect the hazard rate by which the rewrite rules fire. So maybe I am more likely to overdose as my fentanyl level in my system goes up, or something like that. Or more likely to be hospitalized as my viral load goes up. It's a hazard rate sort of thing. You see what I mean? And finally, there's the budding agents that Jenna knows all too well, right? And I alluded to this morning, appropriate enough. So here, agents can come from a continuum, from a stock upstream that represents the general population and turn into agents. So that's another way we're seeking to mesh these. Like ODEs can create agents that then get rewritten. Okay. So one interesting thing about this, which I didn't anticipate, certainly starting, but Chris Brown convinced me of the desirability. So these stock flow models we've been talking about, they can work alongside the ODEs, or sorry, stock flow and rewrite rules can work alongside each other. Are you comfortable with that idea? And in a way, like in any logic context, it's replacing what in any logic we might have an event going off periodically, which manually updates the stock, right? The value of the stock. Instead of having that and then the stock evolving according to flows, now we have like a rewrite rule, maybe produced with a state chart or Petri net, updating the stock flow value. But so these stock flows, or ODEs more generally, but again, I like to, my mind goes to them being produced by stock flow. Where these things are written in is governed by matches, by pattern matching. So you say, when we have this situation, when we have a mother with a fetus, we're going to weave in a representation of how her blood sugar is affected by the weight of the fetus. When we have two, we'll have one weight for one fetus, one weight for another, affecting the mother's blood sugar. So it's like pattern matches now enable and disable stock flow, little stock flow models, which is kind of cool. Okay, and you can have negative application conditions here. Okay, so I don't have time to go into this in detail, but one thing that's pretty nifty about this, I don't know how much you folks remember this, but one bugbear of ABMs is order dependence. So if you implement the game of life and you naively say, well, the first cell will update first, and then the second cell will update in the third, it's going to lead to totally different results than if they all figure out what they're going to do based on the current situation without changing anything of everyone else. What's everyone else's state? I'm going to figure out whether I'm going to live or die. And then they all update themselves without having to look at the other state because they have all that information. Those give two very different things. And one nice thing that Chris convinced me of is the way in which this is categorically put together, it guarantees that within the limits of what are called clashing updates, okay, where there's an inherent clash. There's this update order invariance. It turns out whether you update, it turns out that there's this, it guarantees that it's updated correctly as if it's in lockstep, which is if they're updating at the same time. And to recover that, I'd have to think through and talk with Chris, but that was the gist of that, of his assurance here on the board, that it's independent of the way in which it's defined. We don't have to worry that we artifactually twist how it updates, that there's this guarantee it updates in a way that will commute, whether you do whatever order it happens to compute the updated state, it'll be the same. So it'll commute.
Can you show the previous slide again? Like
This one.
Yeah.
Yeah. So it's basically saying, look, if we update X and then update Y, it's the same as updating Y and updating X. This is very compositional, like very category theoretic. It commutes, the commuting square, right? You do X and Y, it's the same as Y and then X. Do you see what I mean?
Yes.
Yeah. Okay, so a lot of love went into state charts. State charts in Stock and Flow are close to my heart for the design of this system. And Cheyenne has implemented statecharts.jl and has realized even, some simple visualizations for that. So state charts are the primary mechanism I foresee in most of our models that the vast majority of rewrite rules come about. It's through state charts. But they don't compile down to arbitrary Java code like in AnyLogic. They compile to rewrite rules, which are transparent, which are functorial. You can lift them, right? You can lift them. They have nice mathematical properties that can be proven. It has well-defined mathematical semantics compared to, for loops and if statements and in static variables in Java or something. Okay, so Cheyenne's implementation, we've been aiming towards supporting conditional transitions, fires immediately upon a pattern match. This should be quite familiar. Like when this pattern match applies, go from this state to that one. Arrival, when I move, when I arrive, I transition, right? It should be familiar. Hazard rate and timeouts. And where you have guards associated with them, a guard for eligibility, does this rule apply? Or a guard for, does it fire? Like, does it rewrite? Or both. So, and these can be done with a hazard rate, or a rate per unit time, or with a timeout. And basically these guards have some of the flavor of application conditions. Okay. Yeah. Yeah.
So yeah, and our group try the contact rate and timeout. Didn't try the condition arrival.
Right. Yeah. The arrival is not yet, like we have to work on mobility, and that might be something we work on in Edinburgh. But actually, I mean, the mechanisms there, like if you have a graph where, mind you, for like a static network, people are like vertices and edges come into them, right? But if you think about it, a simplistic notion of space can be obtained where people are in places if you have people and there's some relation between people and some vertex. And that relation can change as I move from vertex X to vertex Y, right? That's mobility. And then there may be connectivity from one vertex to another. You can go from this vertex to another. That's the basic idea here with mobility they're shooting at in the immediate term. Of course, we want to move eventually towards geographic stuff and so on, but one step at a time, right? One thing we didn't do was hierarchical state charts. Those can be done in a nice operatic way, but we haven't wanted to go there. Okay. Now, I said earlier that state charts really capture situations where you're not consuming things. By consuming, I mean like they're not really great for saying a vaccine dose and a susceptible person come together to be a vaccinated person. Petri nets are somewhat more natural there, I think. We could maybe twist the charts to handle it, but it just seems, since Petri nets are a nice language, just doing it with a Petri net is probably better. State chart hazard rate expressions, GATLab. This is the GATLab thing, and this is actually a little state chart algebra that Evan helped us mock up. This one, yeah. Okay. Okay, I want to say something about rewriting. And so the underlying rewrite mechanism is you match and then you schedule. Do you remember this issue? Like maybe you match, and it's when that match applies that I am in the effective state. That's when I have a certain chance per unit time of going to a recovered state. Does that make sense? Or if I'm in the vaccinated state, I have a certain chance per unit time of losing immunity, right? So it turns out that so it was some interesting discussion in the hackathon last summer. Should we have timers? Should we have a probability distribution associated with when you leave? Or should we have hazard rates? And at some level, they seem like the same. Like you can convert from a hazard rate to the implied probability distribution. But a hazard rate applies over the next little bit based on the current state of the situation. A probability distribution of when I will leave somehow assumes omniscience of the future, like what future state I will have. That because my future state might affect how quickly I leave. So a hazard rate is kind of like, given my current situation, what's my chance of leaving? That's something I can compute right now. Whereas like in general, probability distribution of when I will leave, often it depends on things I don't have access to. So if we have a hazard rate, now this is quite interesting. If there's a state independent hazard rate, we pre-schedule it when I'll leave, when I would leave via this transition. I don't have to roll the dice every little delta t. I don't have to do it because it's state independent. It's not like it's changing over time. So I can pre-schedule it on a schedule and just say, when this happens, wake me up and make me do that if I haven't, something else hasn't happened to me. Like I didn't disappear. For state dependent hazard rates, we actually do Bernoulli draws over these. We flip a coin every delta t. To figure out, does this happen?
Makes sense. Yeah.
Rather than, because there was a lot of discussion of like, should we schedule it and then reschedule it? No. It's still, if it's dependent on state, just flip the coin every time. Don't get into scheduling and descheduling and very complex, right? Okay. And then there's some question, well, do we reschedule an event that's fired? And there's some interesting things. So there's an event schedule underneath here, okay? And we said like state independent, pre-scheduled, state dependent things, you flip a coin. And if scheduled events are preempted, like the agent dies, disappears, or they leave because they matched a different pattern, they leave the condition that qualified this, you want to remove it from the schedule. Any logic does something quite similar, by the way. And I think in general, discrete event sort of handling like this. Okay, so this is one of the more interesting things, but time is getting short. I will just say, so Chris Brown has convinced me that the way to deal with this, a good, reasonable approach to deal with this, is use rewriting as our main framework, but optimize the heck out of many special cases. Many special cases can be recognized as allowing great efficiencies, and let's make them super efficient. And so we'll have a very general mechanism that will handle all sorts of possibilities, and just 80% of the cases will be really quick. And there are a couple very cool ways of dealing with this that I did not expect going in to the hackathon last summer. But he has put into place some already. So one of the neatest is what's called incremental HOM search. Okay, see, the idea here is, you know the notion of a rewrite rule, right? Rewrite rule, do you remember that? Push out square, it updates the state. See, the idea here, get this. If there are other rules that may need to be scheduled because now they apply, the agent has reached the location, or the agent is next, a susceptible is now one hop removed from an effective, whatever. You might think that, okay, we update the state, now we got to recompute whether all these apply. Instead, he does this incrementally. So you only have to recompute the ones that have changed. He actually has a way of figuring out which ones were affected by the update and not bothering recomputing the others. So it's not like you update the state and now we got to figure out which ones apply. No. We update the state and we know which ones now have to be recomputed, which is incredibly cool. I wouldn't have thought that he could do it that easily, but he can. And he implemented, including, and you can deschedule events that no longer apply. Like you update the state and then you realize, oh, this one that has been pending no longer applies. So incremental HOM search is a key part of CatLab and algebraic ABMs now. Now, there's another thing. So one thing that we haven't talked about among us is this thing called the innate lemma. And I always thought the innate lemma is something really cool, potentially relevant, but I didn't really grok why it could be so valuable. It turns out that you can use it to spot cases where there are no instances of this pattern in the state. Okay. Now, I won't unpack this all right now. I could unpack it for some session of a discussion group. But basically, you can use the innate lemma to say, okay, there's none of them in there, which is kind of wild. But some comments here are made, and basically, look, it gives you a really, so remember this idea of like Tinker Toys, and you have these pieces out of which you can build a bigger part. Imagine if you had a really quick way of knowing that there's none of these pieces which are yay big in there, none of these sticks which are yay big. Then you can rule out needing to match anything which is built up out of this, like as one or two or three of those sticks. If it has any of those sticks, and you know there are none of those sticks around, you don't even bother. You realize there are none of them. There can't be any of them because it's built out of one of them. Or imagine those little, Jenna would probably recognize it, maybe Larissa too. Who knows, Ujia maybe. Those little flags. Do you remember there were these little like plastic flag things for the, you don't for the Tinker Toy? There's these little like yellow. I guess so.
Like you would put into the holes.
Well, you would stick it into one of those sticks, like you'd stick it in between there. It would be like a flag. Okay, so little like triangle, kind of triangular, trapezoidal sort of thingy. Anyway, so there you could say like, if there's no flags, there ain't nothing that has a flag. And it turns out, here's the deal. Every functor is composed of a set of representables. It's a sum of representables, just like every function that we normally deal with has a Taylor series expansion. Every functor has kind of a Taylor series expansion. I think it's called the Goodwilly calculus that lets us do this, but it's a sum of representables. And so if we know one of the representables is gone, like there's none of it, We don't have to worry about, yeah, we don't have to worry about something that requires it. Anyway, it turns out state charts allow us to exploit characteristics as well. With state charts, we have a lot more constraints than for general pattern matching. The patterns have a very specific thing. Turns out there's this thing called in-place rewriting, which you might naively think when you match a pattern, you make an entire copy of the state. It turns out Chris and Evan have kind of figured out a way to do that rewriting in place. So you don't have to make a complete update of the state that copies everything, except for the thing that changed. No, you just do it in place because you know there's nothing that will be badly affected by that. It turns out, oh yeah, this is another cool one. This is another cool one. Get this. Take a load of this. Okay. Okay. So we have an event for n agents. They have an event like when they want to eat goes off at a certain memory list. Are we okay with that idea? Or maybe it's when they fall outside. There's a certain rate, right, of falling, right? Point, yeah, right. 0.02 per day.
No, make the high risk agent.
That's right. So 0.02 per day, 2% chance per day of people falling. And there's 10,000 agents, right? The naive way to do this is like each of those agents figure out, do I fall today? Each schedules, and you've got 10,000 things pre-scheduled in the event, in the queue for when this agent will fall, when Nate will fall. That's a really bad one. When this will fall, when that will fall, right? 10,000 agents, just chock-a-block full of these. Instead of doing that, have an event going off at n times that rate for when the first one will fall. So you just schedule the first. And then you do that, and then you schedule the next with rate n times lambda. You just do that. So instead of each going off with lambda and scheduling n of them, you have it going off with rate n lambda, just schedule the first. You just need one on the schedule. Chris is just like a genius for coming up. It's Chris and Evan, just amazing. Anyway, we could do a bunch of neat things, and I'm just so impressed. It's the mathematical, get this. There's a key high-level point. It's the mathematical invariance of this. The fact that it's completely well mathematically defined. That's what allows these optimizations. We support the general case, but we can optimize the heck out of the special cases because we know mathematically when they apply. And we could use tools like the Oneida lemma or features of the situation to do incremental hump search. So it turns out there are these kind of layers of things, like things that are events that are inevitable, super easy to optimize, like you know exactly when it's going to occur. Things that are memoryless, things that are state independent is a superset of that. You can have something that's not memoryless, but it's state independent, like you will leave in 10 units. But it's not dependent on the state. It's not going to be rescheduled. But then there's a larger one of state independent, and then all transitions. And the point is that these ones that are easily optimized are probably 80%, 90% of transitions. So optimize the heck out of it. And these outer ones, those are maybe a lot of really tricky ones, like when there's a smoker surrounded by a non-smoker surrounded by smokers, how they influence or whatever. Okay. Anyway, this is in code. This is a discrete case. It's amazing to see like these logic about representables, the Oneida lemma, coming to have a coming to the fore here. And again, state charts compile to rewrite rules, and you can optimize. This is in the context of the code base. I won't have time to talk about this, but state charts provide rich opportunities for optimization. So let me give you a really trivial example. All transitions coming out of state S. Maybe state S is confusing. it's infective. And maybe there's a transition out for recovery, there's a transition out for dying of infection, there's a transition out for going to the hospital or whatever. All of them are conditional on remaining in state S, right? If they leave state S, those don't apply anymore. If that particular person leaves state S, it doesn't apply. So they're all conditional on it. If they leave the state, you can DQ all the events for that. For events without other conditions beside the presence of the originating state, can pre-schedule only the earliest of the ones. So if I come in there and I can pre-schedule, I'm going to recover before I die or before I fall or whatever, die and fall or whatever, fall and die, then I can schedule the first of them, right? And it turns out there's all these like special cases that make it really quick. You don't have to do general pattern matching. You use a kind of really slick, quick one, pattern matching. You don't need the full general mechanisms. Okay, we talked about lifting rewrite rules. You kind of get the idea there. Data migrations.jl, the thing I started this session talking about, plays a big role, translating rules from here into a broader context, translating them to a broader context. Okay. Yeah. Okay, fine. So we can kind of bring rules from a smaller context, bring them into a context where we have vertices. These are the susceptible person, infected person, and now we bring them to a context where they have to be on the same vertex, for example. Okay. Okay, yeah. Okay, we don't need to. Okay, what things are not in here? Well, there's a bunch not in here. So I get to put mobility here because that's actually a significant thing. Mobility. Let's talk about a few other things. So model composition. How do we stick models together? Remember stock flow was all about composition, composing them. How do we stick these models together? Well, we have some idea for the sub-modules for like smoking and for like networks and for like space. There we can take the push outs of schemas, but the whole thing about like how could you make one ABM model feed into another? That's an interesting question. Or how could you embed one agent within another? So you have an agent for a person embedded in the community agent. You have a bunch of people embedded in the school agent, right? A teacher and students, right? How do we characterize scenarios and kind of assumptions about those scenarios? How do we characterize observer processes in a way that's not entangled with the model logic? So where we can separately specify scenarios from the model logic, they're separate, they're distinct. We can update one without updating the other, etc. And how do we describe like observing what's going on in the model without entangling it with the core logic? Right now in any logic, they're kind of tangled. Like you have code involving reporting and keeping track of how many have gotten sick, how many times they've been infected. It's all tangled up with how the agent evolves. We should be able to describe them separately. And we should be able to use different observer processes for different stakeholders too. So we can have different stakeholders. Can see different outputs from the model. We can enable, disable certain outputs without modifying the whole model. We should be able to evolve the model and have the observer processes try to migrate with that. Within limits. I mean, if you delete the state chart involving heart disease, you're not going to be able to report how many people have heart disease, but it should realize that automatically and realize this no longer applies. So how to exploit double categories and double theories. You'll see why this has some serious motivations for it next week. How do we do the kind of integration of the ODEs and stuff like that, and together with stochastic transitions? How do we map it to different interpretations? Can we take an ABM and extract a stock flow that's an aggregation of it, like an SIR ABM, and map it to a stock flow? That would be really nice. I mean, it's mathematically totally, the ABM, it should be mathematically well defined. We should be able to, at some level, have a functorial map from one to the other. We have a map between ABMs, converting one ABM to another one, like maybe aggregating the heart disease states into one state, aggregating, microvascular heart disease, macrovascular heart disease into one, cardiovascular disease. Maybe you should be able to have a similar map on the aggregate model of that. But, or mapping, get this, mapping an ABM to a corresponding causal loop diagram that summarizes it, its feedbacks, right? Different semantics, that'll be a nice thing to have. How do we handle mobility? How do we handle the stochastic differential equations, hierarchical models, clear formulation of continuous discrete? So this summer, we're hoping in the Edinburgh hackathon to take on some key ones of these. That's a little bit about where we're going here. So it's a little bit where we're going. We have challenges. We have good partners. We're discovering things. We discover some things that are harder than expected. We discover some things that are much easier than doing it the traditional way. And we're learning how to do it better over time. And how to do it faster, more optimized, more transparent. And I think it's going pretty well. Ultimately, we'd like to bring this together with data sources, data outputs, data sources that might themselves be described categorically. But that's all we have time for today. I hope that gives you some sense of the AlgebraicABMs vision, the AlgebraicABMs story, the AlgebraicABMs, dare I say, saga. Okay? Led by John Buys, theoretically, together with Evan Patterson, Chris Brown, and of course, Zhao Yan playing a far bigger role than I in terms of the implementation, having authored the statecharts.jl and several example models now beautifully using data migrations.jl. But I'm glad to be helping facilitate this too. Okay, that's all we have time for today.